Hello and welcome to the third video of the M3 chapter Circular Motion. Exam question on the screen to get us going. Pause the video now if you've got time and give this a go. Figure 1 shows a hollow cylinder with a diameter 70 centimeters. So there's our radius of 0.35 meters. The cylinder is rotating at a constant angular speed about its axis, which is vertical. As the cylinder rotates, particle P remains in contact with the same point on the rough inside surface of the cylinder. It's moving in a horizontal circle, same diameter. The cylinder makes 2 complete revolutions every second. That is telling me the angular speed. So 2 circles, 2 complete revolutions is 4 pi radians. And we're being told that that is happening every second. The coefficient of friction between P and the cylinder is mu. Find the range of possible values of mu. So what we've got here, if I zoom in a little bit, we've got the particle here. We've got obviously the weight acting downwards. There must be a normal contact force with the surface acting radially inwards, providing our circular motion acceleration. And then there must be friction, because it's rough and we're trying to find mu. If friction was acting downwards, then there would be nothing stopping it from sliding down. Friction must be acting upwards, balancing the weight, holding it in place. If that friction is not high enough, then it will slide downwards as it rotates. If that friction is high enough, it will stay in place. We know that our maximum friction is equal to mu times r. So in this situation, assuming it doesn't slide down, the friction is equal to mg. So the friction, and therefore mg, must be less than or equal to mu times r. Now our circular motion here, we know that r is the only force acting inwards. So we've got r is equal to mass times acceleration. And the acceleration is r omega squared, because I know omega and r in this situation. So putting all of that together, I've got mg must be less than or equal to mu times r, which is m little r omega squared. M cancels out. I'll switch it around. I like my unknown on the left. So mu is greater than or equal to g over r omega squared. But we know all of those. Let's approximate g to 9.8. R we know is 0.35. And omega is 4 pi. We're squaring that. And if I throw all of that on my calculator, I get 0.177 ... And I like 3 significant figures for mu, but really, because I've used g as 9.8, I should round that to 2 significant figures, 0.18 to SF. So mu must be greater than or equal to 0.18, otherwise it will slide down as it rotates. In this video, we're looking at motion in vertical circles. This is a little bit different because in vertical circles, the effect of gravity has more of an impact. In horizontal circles, it was generally just being used to balance something in our resolving, but in vertical circles, if I put a little circle on the side here, if this is happening in the vertical plane, as the particle goes up this way, it must be doing work against gravity. So as it goes up, it is gaining gravitational potential energy and losing kinetic energy as it sort of fights against gravity, as it were. At the top, the gravity is trying to pull it down, obviously, as it continues around like this. The downward gravity is not doing any work in this instant because it's perpendicular to the motion. Remember, the motion is tangential in that instant, and then as it comes down, of course, it is gaining kinetic energy and losing gravitational potential energy. And then down at the very bottom here, this is where our tension is going to be at its greatest, because it is having to hold up against the weight as it comes around, and it's got its least amount of gravitational potential energy. If you take this level here to be 0, then it's got 0 gravitational potential energy, and it's got its maximum kinetic energy. If that hasn't been obvious, in vertical circles, what we tend to do is switch to an energy point of view. Gravity is the only force doing work though, although we've got the tension here. At every point, the tension is acting radially inward, and at every point, the direction of motion is perpendicular to that. And you know that a force perpendicular to the direction of motion does no work. So the only thing doing work here is gravity, assuming of course no air resistance. One last thing with the notes is to reiterate something I've already said. At the top here, this is where the speed of the particle will be at its lowest, and at the bottom here, this is where the speed of the particle will be at its greatest. Now there's something extra to say on this. We've got greatest speed will happen as the particle passes through the lowest point, and lowest speed will happen when the particle passes through the highest point, and at that highest point you must have some speed, otherwise you won't be able to complete a full circle. In addition, if it's on the end of a string as opposed to a rigid rod, if it's a rigid rod, obviously this is not going to collapse, it's rigid, it will stay straight. All you need is some speed to get past that balance point and continue round down here. But due to the nature of a string, you know, in a string, if there's no tension, basically the particle is just going to fall straight down like this, or as a projectile moving under gravity. So when you're dealing with a string rather than, say, a rod, you must have tension greater than 0 for this thing to keep moving at the top of the circle and therefore complete a full circle. This will come up in our examples. First one here, a particle of mass 0.4 kilograms is attached to one end A of a light rod AB of length 0.3 meters. The rod is free to rotate in a vertical plane about B. So B is the center here. We've got the rod, which is rigid, particle A on the end. It has a mass of 0.4 kilograms. And I should have finished reading the question. I'm going to have to redraw that because the particle is held at rest with AB horizontal. The particle is then released. Okay, let me get rid of that. We've got B here. AB is horizontal. It's held at rest. So initially V is 0, and then it's released. Of course, it's going to come down and around like this. Calculate the speed of the particle as it passes through the lowest point of the path. So that's down here. We call that C. And then we also need the tension in the rod at that point. Going straight into our energy point of view, I'm going to say at A, using this level as h equals 0, then the height at A, switch into a different color here, is just the radius of the circle, i.e. the length of the rod. So this is 0.3 meters. So at A, my gravitational potential energy is equal to mgh, which is 0.4 times g times 0.3. My kinetic energy is a half mv squared, which is 0 at A. So my total energy in the system is 0.12 g. At C, that is still true, but the gravitational potential energy is now 0. So the kinetic energy must equal the total energy, 0.12 g, which is equal to a half mv squared. The mass is still the same. I didn't really need to put that in. So 0.12 g is equal to a half times 0.4 v squared. That gives me 0.6 g is equal to v squared. And throwing that on my calculator again gives me 2.4 meters per second for v to two significant figures using g as 9.8. Part B, the tension in the rod at this point. Put in the rod. T mg there. This is where we switch back to circular motion. The energy approach isn't going to help me in this case. I've got tension and mg, and it kind of looks like they're balanced, but don't forget in circular motion there must be an acceleration radially inwards. So they're not balanced because this must be great enough both to stop the particle from falling downwards, but also to provide enough force for the acceleration that's connected to the circular motion. So we've got an overall force is equal to mass times acceleration. The overall force is T minus mg, and that must equal mass times, in this case, v squared over r, because we know what v is at this point. So the tension is equal to the mass, 0.4, times v squared, which is 0.6 g, putting it back into exact form, divided by r, which is our length of the rod, 0.3, plus the mass again, times g. That gives me a total of 1.2 g, 12 newtons to two significant figures. So one thing to be wary of here is that the tension will be changing as the particle goes around. At this point, the tension didn't have to do anything with the weight, but as it comes down, the tension's increasing, and as it comes all the way around up here, potentially the tension will get down to 0 at the very, very top, but either side of that point, it would have to be greater than 0, as we said before, in order to actually keep going around. We'd have to have speed at the top for it to be able to continue and make a full circle. So be aware of that. Tension will change as it goes around the circle, which was generally not the case in horizontal circles. Example number 2. Same setup, a particle of mass 0.4 kilograms, still attached to A of a light rod AB, still length 0.3. The rod is still free to rotate in a vertical plane about B. So we've got everything exactly the same here, initially. The rod is hanging vertically with A below B, there we go. When the particle is set in motion with a horizontal speed of u meters per second. Determine an expression for the speed of the particle when the rod is at an angle theta to the downward vertical. So I'll keep it simple, make that less than 90 here, through B. So the question is V here. And again, we're going to look at energy here, because initially, if I take this point here to be my h equals 0 level, then I've got 0 gravitational potential energy at A, and the kinetic energy is equal to a half mu squared. Call this point C. At C, we have a half mv squared for the kinetic energy, which we don't know yet, because we don't know what v is. That's what we're trying to find. And the gravitational potential energy is mass times gravity times height. So I'm going to need to know the height. That is this bit of height here. To find that, I'm going to do this bit first, because we can do that using the length of the rod, 0.3 cosine theta. And then this little bit here that we actually want is 0.3 minus 0.3 cosine theta, which is a bit messy, but we're going to have to use it nonetheless. So our mass here, we've got a 0.4 times g, I'll leave as g for now, times h, 0.3 minus 0.3 cos theta. And the whole point here is that the total kinetic energy of the system doesn't change. So we've got a half mu squared over here, and over here, a half mv squared plus 0.4 g times, let me write this slightly differently, 0.3, 1 minus cos theta, and then I can combine those decimals in a moment. Now, from what I just said, the totals don't change. We're not losing anything to friction or air resistance. We've got a half mu squared must equal a half mv squared plus 0.12 g 1 minus cos theta. And I'm just about to undo what I've done there, because the 0.4 here can cancel with this m here. So that's back to 0.3. I'm going to multiply everything by 2 and rearrange it slightly, so I get v squared is equal to u squared minus 0.6 g 1 minus cos theta. And as horrible as that looks, we're now going to have to square root that to get v. Square root of u squared minus 0.6 g 1 minus cos theta. And that is our expression for v at this point here. I hope it's obvious that that should be dependent on the initial speed that's given, and also theta, how far around the circle it has travelled, because it will be losing, as you can see by the negative, it will be losing speed as it goes up and does work against gravity. Now there is a second part to this, and the second part says find the minimum value of u for which the particle will perform a complete circle. This is what we were saying earlier, that if we want a complete circle, by the time it's got up here at the top of the circle, it needs to have speed to get past that point. So if v is equal to 0, that's going to be a bit of a problem, although we do often use that as the minimum value. What that should really be is v greater than 0. So I'm going to set this expression here as greater than 0 and find u at this point, remembering also that at this point I can see what theta is going to be. Theta is going to be pi, or 180 degrees. So we've got v is greater than 0, or you might see greater than or equal to. So that's the square root of u squared minus 0.6 g, 1 minus cos theta, greater than or equal to 0. I can square both sides without any problem and bring the negative expression onto the right. I can also now put in pi here, or 180 degrees, depending on whether you're working in radians or degrees. That is a negative 1, which gives me a 2 in the brackets. So this becomes a 1.2g. So u must be greater than or equal to the square root of 1.2g, and that must be a positive because u is a speed, not a velocity. So you could argue that the minimum value should be this, or I guess you could argue that it should be something very close to this, but it shouldn't actually be this. Maybe I shouldn't have that equal sign there, because if it was equal to that, then the speed would be 0 at the top. And if there was no speed at the top, then you could argue for a rod, it would just be balanced. As unlikely as that seems, the slightest disturbance from that equilibrium point would bring it this way or this way. In that situation, I would let the question, or the exam question specifically I'm thinking about, let the exam question be your guide as to whether it wants a strict inequality or if it is looking for that little equal sign there. Third and final example also has the same setup, but with one important difference, and that is that we're using a light inextensible string instead of a rod. So we've got mass 0.4 again, length 0.3 again. We've got point B as the center of the circle. The particle is hanging in equilibrium. Here it is, when it is set in motion with a horizontal speed, again, of u meters per second. We're determining this time an expression for the tension in the string in terms of u when it is at an angle theta to the downward vertical through B. So very similar to the previous question in terms of the setup. There's theta, and as we mentioned previously, the tension is going to change as the particle moves around the circle. So I'm going to have to add on here mg for the weight, but at this point, let me call this C, the tension is not as big as it was here, because here it has to balance all of the weight and provide for the acceleration for the circular motion. Here it's got to provide for the acceleration for the circular motion, but it's only balancing a component of the weight. We'll come back to that later. Initially, very similar question is going to have a very similar approach. We want an energy approach here. From here at A, we've got gravitational potential energy equal to 0, because I'm going to make this my h equals 0 point. Make that clear in your exam questions, by the way, wherever your h equals 0 point is, because some people might prefer to have that here and to have this lower, or to have it wherever the particle starts. If it starts here, maybe you want it here. Make that clear. Where is your h equals 0 level? So if I put that there, gravitational potential energy at A is 0. The kinetic energy, again, is a half mv squared, where in this case we know that v is u. At C, same as before, we've got 0.3 on the length, so this distance here is 0.3 cos theta, so the little distance here that I need at C, h is equal to 0.3 minus 0.3 cos theta, same as before. So the gravitational potential energy is equal to the mass times gravity times 0.31 minus cos theta. The kinetic energy is equal to 1/2 mv squared, and it's all so similar that I'm going to jump to what I know v squared is. That's u squared minus 0.6 g 1 minus cos theta from work on the previous question. On the previous question, that's where we wanted to stop, or we square rooted it, but that was basically the end point. In this question, we need t. So here, we do need to have a resolving radially as well. If I resolve the weight in this direction, I get mg cosine theta, because this angle here is the same as this one here. And I'm resolving in that direction because this is the direction of our acceleration to provide circular motion. And again, the t must be greater than this because we've got that acceleration. So using F equals ma, my resultant force is t minus the component of the weight in that direction. Has to equal mass times acceleration, and I'm going to choose v squared over r because we've got v squared here as this expression. Substituting that into here is going to give me t with all this other stuff that I'll need to simplify if I can. Running out of space a bit here, but we've got m over r times v squared, so that's u squared minus 0.6 g 1 minus cos theta minus mg cos theta on this side, and a t. Trying to squeeze it in this little space here on the right hand side, that gives me mu squared over r minus a 0.6 g m over r plus a 0.6 g cos theta m over r. On the left is still t minus mg cos theta, so if I move that mg cos theta onto the right as well and replace r with what I know r is, 0.3, and m with 0.4, we can get t is equal to 4 u squared over 3 minus 4g over 5. The 0.6 times by the 0.4 that I couldn't quite squeeze on there, divided by 0.3, that gives me a 0.8. But then I'm adding one lot of mg, so that's another 0.4 on as I bring that over the other side, which gives me 6 over 5 lots of cos theta times g. And that here is our final answer for t in terms of u and theta. Part B says find the minimum value of u for which the particle will perform a complete circle. Now the difference here between the rod and the string is what we said at the very beginning of the video, that for a rod we want the speed to be greater than or equal to 0 at the very top, but for a string we need the tension that we found here to be greater than or equal to 0 at the top. So I'm going to take this expression, make this greater than or equal to 0, and solve it. So here the key point is t is greater than or equal to 0, and again you could argue that it should be greater than rather than greater than or equal to, but I don't think it's quite such a problem here if the tension is equal to 0 at the very top of the circle, so long as the velocity is not also equal to 0. Then you'll continue past that point, the tension will become greater than 0 again, immediately after the very highest point of the circle. Saying all of that, I've forgotten the expression, so 4 over 3 u squared minus 4 over 5 g plus 6 over 5 g cos theta greater than or equal to 0. We know theta at that top point is going to be pi radians, or 180 degrees, which is minus 1, which gives us 4 over 3 u squared minus 4 over 5g minus 6 over 5g. Rearranging that gives me 2g on this side, 4 over 3 u squared. So u squared must be greater than or equal to 3 over 2g, and u greater than or equal to the square root of 3 over 2g. This then being the minimum value of u for which the particle will perform a complete circle. So those are the 3 examples. I wanted to finish with another exam question. So we've got a particle of mass 3m is attached to one end of a light inextensible string of length a. The other end of the string is attached to a fixed point O. Particle is held at the point A, where this is horizontal. It's projected vertically downwards with speed u, and it moves in complete vertical circles. So at the top we'll have t is greater than or equal to 0. Now let me explain the reason I've been using this symbol throughout the video rather than a strict inequality is because it's got it here in this exam question. That's the only reason why I have not been using a strict inequality. So what we need to do here is show that u squared is greater than or equal to 3ag. Now having this completely out of the blue, it might not be obvious how to start, but given that we've just gone through a question very similar to this, it's probably more obvious. What I'm going to do in this case, just to mix it up a little bit, and because I do like having zeros for my gravitational potential energy, I'm going to make h equals 0 here, where we're starting. So that I can say at A, gravitational potential energy is 0. And the kinetic energy is a half m. Now I'm going to have to be careful here. This is 3m times v squared, and it's a u squared. Showing that u squared is greater than or equal to this requires me to start with this inequality here at the top of the circle here. So I'm going to call this B, and tension is still this direction, but so is the weight. So at B, gravitational potential energy is not 0. That's mass 3m times g times the height, which is 1 length of the string, a. The kinetic energy here is equal to a half 3m times v squared. If this were a rigid rod, I would be using v is greater than or equal to 0, and that's where this v would be. But I need to go through this to find v squared and then also resolve to find t. So we're equating these because the total energy at A is 3 over 2 mu squared, and the total energy at B is 3 mga plus 3 over 2 mv squared, and those totals have not changed because there's no resistance of any kind. I can cancel the 3m from each term, multiply everything by 2 and rearrange, gives me v squared is equal to u squared minus 2ag. This is useful because now I need to resolve vertically, still at B. So at B I've got t plus mg, both acting in the same direction, is equal to mass 3m times the acceleration. Obviously I'm going to use v squared over r, form of acceleration in this case, and I know r is a. Substituting in for v squared gives me 3m over a times u squared and minus 3m over a times 2ag. And the reason why I circled this at the beginning is because I know I'm prone to write m for mass, which I've done here. Let me get rid of this plus and just squeeze in a 3mg there. That's better. Now the a's there cancel, so we get a 3m u squared over a minus the 6mg from this minus another 3mg from here is minus 9mg overall for t. And of course the whole point of doing all of that was so that we can now set this greater than or equal to 0. Rearranging, we get 3mu squared over a greater than or equal to 9mg. That cancels, that becomes a 3 with that cancelled. We get u squared greater than or equal to 3ag as required by the question. Part B, given that the greatest tension in the string, which remember happens at the lowest point where we've got the weight here and the tension here, is 3 times the least tension in the string, and remember that happens at the point that we've got, point B. So this T is the minimum tension, this expression here. So that's going to be useful, but we're going to have to do most of this all over again with the point here. Let me call that point C. So at C, now a lot of this is still true. I'm still going to use A as my starting point. I'm still going to use the height there as 0, so the total energy is 3mu squared over 2. The difference at C compared to B is that instead of A being the height, it's going to have to be a negative A. That's a consequence of me having chosen this as my 0 level. You could have chosen this as your 0 level, in which case this would have had height A, and this would have had height 2A. You would still have got this result, and this might be a slightly easier part to do if you had done that. But I still like getting a 0 in there. So my total energy is still 3 over 2 mu squared, and the gravitational potential energy is now negative 3mga. Kinetic energy is still 3 over 2 mv squared. That was very general. When we equate these, we get 3 over 2 mu squared must equal 3 over 2 mv squared minus 3mga. So the only difference here is that this positive is going to become a negative, which means this negative here is going to become a positive. So overall v squared is equal to u squared plus 2ag at C. But I need to continue. I need to do the same as we did here. We need to resolve again to find the tension. So resolving vertically, and this also is very similar but slightly different because our tension is acting in the opposite direction to the weight now. So our resultant force, T minus 3mg, is equal to 3m times v squared over a. And v squared is this expression instead of this expression. So this is going to give us a T max, maximum tension. And again, it's going to be very similar. We're going to have a 3mu squared still, but this will be a positive. And then when I move this over the other side, that will be a positive as well. So this symbol will be plus 9mg. So it's very similar. We get 3mu squared over a plus 9mg. Having done all of that work, we can now say that the greatest tension, this thing, is 3 times the least tension, this thing. So over here, to sort of finish this off, we can say 3mu squared over a plus 9mg is equal to 3 times the least tension, 3mu squared over a minus 9mg. Expanding this out, we get 9mu squared over a minus 27mg, 3mu squared over a plus 9mg over here still. Rearranging, that will give me 6mu squared over a and 36mg. The m's cancel, the 6 can simplify, the a comes over, and we get 6ag is equal to u squared, again as required in the question. So there's a full exam question for a vertical circle, and I hope you can now attempt the questions from exercise 2D. And maybe I'll see you in the final video for this chapter.